All right, let's just jump right into it. Have you ever actually thought about the magical mystery of a broken light bulb? You're sitting in the living room, a lamp suddenly burns out, but boom, the TV stays on, the fridge keeps humming, and the kitchen lights are totally fine. Why doesn't your whole house just plunge into darkness? Today, in this explainer, we're going to unpack exactly how that works. We're turning you into a master of electrical circuits. To answer that, we've got to introduce the absolute hero of our electrical story. Enter the parallel circuit. We're going to break down exactly what it is, how it ticks, and honestly, why it's the gold standard for our modern, everyday lives. By the time we wrap up here, you'll have a crystal clear understanding of the science hiding behind literally every light switch in your house. So, here's our roadmap for today. We'll start with a welcome to parallel circuits, look at their anatomy, and hit the big three rules. Then we'll dive into solving some circuit math, do a quick series versus parallel comparison, and wrap it all up with real-world applications and a recap. Let's get to it. Okay, Section 1, Welcome to Parallel Circuits. Let's lay down the formal definition first. A parallel circuit is an electrical circuit in which the components are connected on separate branches across the same voltage source. But okay, what does that actually mean? The crucial takeaway here is that instead of a single, lonely path, electrical devices sit side by side. They create multiple, completely independent pathways for the current to choose from. So rather than forcing every single electron to squeeze through one wire and one bulb, the current actually has options. Moving right along to Section 2, Anatomy of a Parallel Circuit. Now take a look at how this is laid out. Notice how every single bulb has its very own independent, complete loop going right back to the battery. If you trace the line from the battery, you'll see the path actually splits. One path goes to the first bulb and back, another goes to the second, and a third goes to the third. If that battery supplies, say, 24 volts, every single one of those bulbs is tapping directly into that main power line, no sharing required. And this setup brilliantly illustrates what we call the rule of independent operation. Think about it. If one bulb breaks, or if we open a switch on just one of those branches, the others just happily stay lit. Why? Because their specific pathways are totally uninterrupted. The electrons literally just ignore the broken path and keep flowing through the branches that are still closed. And yeah, that is the exact reason your house doesn't go pitch black when one single bulb gives out. All right, Section 3. This is absolutely crucial. The big three rules. Let's start with rule number 1, voltage remains the exact same across every branch. Because every single branch connects directly to the power source, well, if the battery supplies 24 volts, every branch gets the full 24 volts. In math terms, the total voltage equals the voltage of branch 1, which equals branch 2, and so on. They don't have to share a thing. Everybody gets the full electrical pressure. On to rule number 2, current splits and adds up to the total. Picture the current leaving the battery and hitting a junction where it divides. The total current is simply the sum of all those separate little branch currents. So if 3 amps flow down the first branch and 2 amps flow down the second, the battery has to be supplying a total of 5 amps. The current literally just divides itself up among the available paths. And finally, rule 3, adding branches actually decreases total resistance. Now, I know this is a super counterintuitive fact. Adding more resistors in parallel actually makes it easier for the electric current to flow. This trips up a lot of students, honestly, because you'd naturally think adding more obstacles would, increase the resistance. But because they're on separate branches, you aren't adding obstacles to a single path. You are creating entirely new paths. Let's make this crystal clear with a quick analogy. Imagine being in a super crowded room. If you open 3 doors instead of just one, people can exit much faster, right? More branches literally mean less overall resistance. Even if a new door is super narrow, hey, it's still an extra exit. In a parallel circuit, every new branch, no matter how much resistance it has on its own, provides an additional way for the current to get through. And that drops the total resistance of the whole system.
Which brings us to Section 4, Solving Circuit Math. Don't panic, we've got this.
By breaking the math down into 3 simple, logical steps, solving circuit problems with Ohm's law becomes an absolute piece of cake. First, we just lock in our voltage. Remember, it's the same everywhere. Second, we do a special little fraction trick to find our total resistance. And third, we calculate the current for each individual branch. Let's actually see this in action. Okay, step 1. Since our battery here is 9 volts, we instantly know that all 3 of these resistors receive exactly 9 volts.
It completely doesn't matter that one is a massive 10 kiloohm resistor and another is a tiny 1 kiloohm resistor. They're all plugged directly into the 9-volt source, so boom, they all get 9 volts. Step 1, done.
Now for step 2, finding total resistance. We use this specific formula. Instead of adding the resistors up directly, we add their fractions, their reciprocals. So 1 over the total resistance equals 1 over R1 plus 1 over R2 and so on. And here is a fantastic little trick to check your math. The resulting total resistance will mathematically always be smaller than the smallest resistor in the group. Because we're adding reciprocals, the total resistance of our 10K, 2K, and 1K resistors is mathematically guaranteed to be less than 1 kiloohm. Pretty cool, right? All right, let's move to section 5, series versus parallel circuits. This side-by-side comparison perfectly highlights the core differences. Series circuits force everything to share one single path, while parallel circuits generously give full voltage and multiple paths to everything. In a series, if you add more bulbs, the voltage gets divided and the bulbs get super dim. But in parallel, you add a bulb on a new branch and it gets the full voltage, shining with consistent, bright glory. And obviously, if a series circuit breaks, the whole thing goes down. A parallel circuit just keeps the party going. And just remember this really fascinating distinction. Adding loads in a series makes things harder for the current. The total resistance just adds up, making the current smaller and smaller. But adding branches in parallel makes the current's journeys significantly easier. It drops the total resistance and actually pulls more total current right from the battery. Finally, section 6, real-world applications and recap. Parallel circuits are absolutely the champions of our homes because they let all our appliances work totally independently. Though, we do have to watch out for the more complex wiring and, well, higher power bills. Every single time you plug in a new device, you're adding a new parallel branch. That means overall resistance goes down, and the total current being drawn from your house's power supply goes up. Draw way too much current, and you might just trip a circuit breaker, which, by the way, is a safety device specifically designed to protect you from those huge currents. Let's lock all of this in. If you take away anything from this explainer today, please remember these 3 golden rules for parallel circuits. Same voltage across all branches, split current that adds up to the total, and decreased overall resistance as you add more paths. Master those 3 rules, and honestly, you've completely mastered the heart of electrical circuits. So, I'm going to leave you with this final thought. Considering the slightly more complex wiring and the potential for much higher power consumption, why do you think household electrical wiring overwhelmingly uses parallel circuits instead of series circuits? Seriously, think about that next time you flip a light switch. Keep exploring the wonderful world of science all around you, and thanks for joining me on this explainer.